Okay, this is part one. This is me explaining what homeostasis is. So we're going to talk about homeostasis, how it works in the body, kind of the automatic response, and then some of the different factors and feedback loops that we have. So the word homeostasis means one, homeo means same, stasis says remaining in the same state. So homeostasis means to remain in the same state. So what does that even actually mean? So right here, this dotted line represents where your body likes to be. This right here represents the varying part of that. So we call this dotted line the set point. An example of that would be your body temperature. Your body likes to stick around a specific temperature, and even though outside factors like cold or hot or whatever will offset it a little bit, your body will compensate to keep you at the same temperature. And so that normal varying point is called your normal range. So your body's trying to stay around the set point, and the normal range is where it can offset. And so in a typical homeostatic, like a reflex control, would go like this. Okay, it gets cold. Your body does something, it shivers, it starts, I don't know, metabolizing stuff, and it'll bring your temperature back up. Okay, maybe it gets hot where you're at. You're wearing a sweatshirt, so you get hot. Then you start to sweat a little bit, and it brings it back down. So it's kind of this it can go up and down, but it will stay around the set point. And so how that works is it goes like this. You have a stimuli. And that stimuli is a certain change. In that scenario, so it's really a change in environment. Internal or external environment, okay? What that's gonna do is that stimuli is gonna hit a receptor. This detects the change, okay? That receptor is then gonna take that change to the control center. Most of the time in your body, that is the brain. The control center is going to dictate a response. Okay? Then it's going to send an effector. And that is going to fix the response. It's kind of like a hitman or something that the controller sends. Okay, so going from the receptor to the control center. That'd be like if I touch my finger, it's gonna send a response to my brain that something just touched my finger. That is what's called an afferent pathway. I think of that A as it's arriving. It arrives at the brain. And then going from the brain to, say if I wanted to move a muscle, it's gonna go from the brain out to that muscle. That is an efferent pathway. So it's going away from the control center in this case. And it's going to the effector. So efferent goes to the effector. I think of that E as exit. Exit the brain. Okay, so let's think of another scenario. Say Well, I think you got the point. The temperature is a good example. I'll give you another one as I explain what's called feedback loops. Okay, a feedback loop looks something like this. There is something that happens, and it takes it down. A positive feedback would be if that never got fixed. Okay? Does not fix the stimuli, the detected change. Negative feedback is a perfect response. Something happens and your body responds perfectly to bring it right back to the set point. So, fixes variation. And then there's something that's called an inadequate negative feedback, which means it would be like this. Your babysitter, you hire a babysitter and you're like, okay, watch the kids, keep the house safe, keep it clean. And the kids are making a mess. The babysitter is doing it the best that she or he can in this case to keep the house clean and do her job. But, it just keeps getting worse. The house is getting dirty, stuff's getting everywhere. So there is a response. There is the response that we're hoping for, but it's not fixing the problem. And so, trying, but not working. Okay, there are certain cases where you'll see a graph, and you can interpret how that actually works. So, going back to this set point, there would be, say, let's call this one your blood pressure now. Say you cut your finger. You cut your finger so that your blood volume goes down. So this is blood pressure. You cut your finger, your blood pressure starts to go down. Okay? And then there's something, let's say on this graph, that this is your heart rate. And this is your vasocontraction. So the way that your veins get smaller and stuff. So your veins get smaller, your heart rate goes up. What that's gonna do is bring it back up. So that would be an example of a negative feedback. A positive feedback would be if your heart rate stayed the same. So heart rate stays the same, this stays the same, and it just goes like this, it just drops. Those effectors are not doing their jobs. Sometimes that's a good thing though. So for instance, in blood clotting, your blood starts to clot, it keeps you from bleeding out, and it's gonna send sometimes more than what's needed, just so if you have a super thin blood clot, what's gonna happen is it's just gonna blow again. And so by having a positive feedback, it's kind of overfilling it, overdoing its job, it's gonna keep that from happening again. Yeah, that's part one. Okay, this is part two where we go over the transport part of this. And so I have a diagram to kind of help me. And so this is all talking about diffusion. And so the first question that's really asked is if it needs energy or not. So if it doesn't need energy, it's considered passive. Passive means it doesn't really do anything, right? And then there's active. And so the two different types of passive transport are what's called simple diffusion and facilitated diffusion. And what that really means is doesn't need help or not. Facilitated diffusion gains help from something to get things across the membrane, while simple diffusion does it by itself. So in order for it to go across the membrane by itself, things have to be small, nonpolar, and nonpolar. And so the reason it's like that is because a cell membrane is made of a phospholipid bilayer. And this right here is hydrophobic, which means that if something's nonpolar and small, it can pass easily through that whole thing. Versus if it is polar or ionic, it can't. And that's the difference between the facilitated. The facilitated can pump ions and things that have charges or that are a little bigger through this membrane. And so there's two different types of facilitated. There's carrier and channel related ones. And so their channel is where there's kind of an opening in the membrane and it's highly specific. So there's like it's like a bouncer at a club. It's not gonna let things that aren't supposed to be going through so it can be specific. And so there's a few different types of channel. There's voltage, mechanical, leak, voltage, mechanical, leak, and ligand. And the way that these work is for voltage, there's a certain concentration in the solution, and once it becomes concentrated with enough ions and stuff, it'll create a charge, and that charge will then open a gate. And so that channel is open. So sometimes these are called gated because the door will open to the channel. Mechanical is when there's pressure or it gets like squeezed and the channel then opens up. Leak is exactly what it sounds like. Stuff's just slowly kind of falling through that channel. And ligand, there is a ligand that comes in, and you can think of it kind of like a pressure plate. As soon as it goes, that opens up. And so the difference between these two is their rates. Simple diffusion, because it's not reliant on a protein to help it, it becomes linear. And so the rate becomes faster according to concentration. And this one, the rate will change with concentration, but as soon as it hits a certain point where all the proteins are being used and all the channels and like all that, it kind of has a maximum amount that it can let through. And so it goes like this, it goes up, and then it kind of flattens out. It almost looks like an asymptote. So you can calculate rate right here. So rate equals, this is the diffusion coefficient. And that takes into factor kind of the things that we were talking about make it easier to diffuse. This is surface area. This is change in concentration. And that is the thickness of the membrane. Okay. Now we're going to move over to active transport. Active transport is split into two as well. There's primary and secondary. And essentially the main difference is these ones will pump with a concentration and it will pump with a gradient. These ones can pump completely against a gradient. And in order to do that, you have to have energy. Think of it as like you have a bucket of water and you're trying to take it from the bottom floor to the top floor. It can't fall kind of like this one does. It has to be carried up. And so that's where the energy comes in. In primary, it directly uses ATP. And I'll show you how. This is the sodium potassium pump. What happens is there's this pump right here, ATP pump base. And what happens is this is the extracellular side, intracellular side. The potassium will come through, and what's going to happen is this phosphate is going to fall off and it'll have a conformation shift. And once a conformation shifts, the potassium comes out, the sodium comes in, and then an ATP comes and it binds to that site and it causes a conformation shift again. The sodium comes out, the potassium comes in, and basically it can pump until there's a huge amount of sodium on this side and potassium on this side. So it can create a gradient. And so with that created gradient, that's how secondary transport works. And so secondary transport will take one of these sodiums, and this intracellular side, wants the sodium so bad that it's gonna allow sodium to bring a friend. And that is called symport. So symport is when two of them come together. One is going with the gradient and it pulls it with it, and the other is antiport, and that's just the opposite. In order to get one, you have to have it switch places, and so it doesn't necessarily, it will go against the gradient, but it's one of them is getting fueled by the concentration gradient, and so that's how it works. And it uses that kind of indirectly by working off of a different concentration. And so those are the different types of transport, and I hope that helps. All right, this is the third part of the video where we explain what osmolarity is. Okay, osmolarity is, well, let's talk about the difference between what osmolarity is. This pen doesn't work. What osmolarity is. So, osmolarity versus regular molarity. If I have 1 mole of sodium chloride, if I put that in water, what's going to happen? The sodium chloride is going to fall apart into different ions. And so it really it turns into 2 osmoles. And so that's the difference, is molarity is like 1 mole of a molecule, and osmolarity is basically what that'll turn into in the liquid. And so how many particles of solute it is. Okay. Now let's talk about the difference between osmolarity and tonicity. If you have, we learned diffusion just a second ago. Say you have a certain amount of particles on the outside of this cell. And you have the same amount of particles. So osmolarity, you can think of it as like a concentration. So since these concentrations are the same, their osmolarity would be the same. And so osmolarity in this sense is essentially like a comparative term. So osmolarity can be isoosmotic, hypoosmotic, which means less, or hyperosmotic, which means more. So if I added dot on the outside, that means the solution would be hyperosmotic to the inside of the cell because there's more. And what that is like basically a cause, and the effect would be what's the tonicity. Tonicity would be like the firmness of, or like the way that the cell, the state of the cell. And so if the osmolarity of the concentration on the outside is less or more, in this case it's more, then the water is going to want to flow out of the cell and into the extracellular space. And so it wants to do that because it wants to dilute it. It's the diffusion. It wants to dilute it so that the concentrations are the same. And so if the concentrations are the same, they might not be at the same level. And so there might be, in this case, there would be more water flowing to the outside, so there would be the same concentration, the same dilution. And so that's how kind of how the diffusion works. But if it's permeable, which means there's, say I add a solution of dextrose. These will go to the inside. And in the case of dextrose, it'll get metabolized. And so for a sec, it would be hyper, the osmolarity would be hyper, but then these would go away. They go in the inside, they get metabolized in glycolysis, and then it'd be isotonic, because nothing happens. But if you say I have something like a substance like urea. Urea would flow in between until there's the same amount of it on the inside and the outside. So it really depends on the concentration or the solutions that you use. So, scenario, I give you a normal cell sits at 300 milliosmolars, and if I give you a 5% dextrose, this is what it'll look like. So that's inside the cell. I put 300 milliosmolars. And what's going to happen is the dextrose is going to go in, it's going to get metabolized and disappear. And so it was isotonic, and now it becomes, the cell becomes hypotonic because the water is going to go in to try and dilute this so that it's the same. Thank you.